To learn more about earning college credits with study hall courses, go to gostudyhall.com or click the link in the description. The world is full of random and irregular things, like, say, the way mice run. And even though programming loops usually work with tedious, repetitive tasks, they can also help us with more random things, like radioactive mice. Loops let us repeat the actions of some piece of code as many times as we need, without having to explicitly write out the code over and over again. And loops can even adapt to changing circumstances, handling new data and stopping as needed. This episode, we'll see how to apply this handy programming tool to the plight of our long-suffering rodent friends, the radioactive mice. I'm Sabrina Cruz, and this is Study Hall, Code and Programming for Beginners. Previously on the radioactive mouse dilemma, after nuclear disasters like power plant failures, dangerous radioactive material can pile up in natural habitats. These materials stay radioactive for a really long time, and we saw that the fate of a small animal, like a mouse, is mostly determined by how much material it eats or gets exposed to, at least in our simplified scenario. A tiny amount of exposure, and the mouse, alongside its environment, will be relatively fine. Too much, and the mouse will die before it gets anywhere fast. But there's a middle ground where the mouse can spread the radioactive material far and wide as it poops or gets eaten by other animals. So a good question to ask is, how far will a radioactive mouse travel over a certain period of time? Predicting the exact motion or behavior of a living creature, even something as small as a radioactive mouse, is pretty tricky. The mouse might come across a rock slide blocking its path, or be tempted by a berry dangling from a bush, or run away from a snake, or you get the idea. To account for details like this, ecologists and other scientists sometimes use a concept called Brownian-motion to model the movements of certain animals. So we'll use it as a simple model for our radioactive mice. The general idea of a Brownian-motion model is that every minute, our mouse will pick a random direction to head in and then travel a random distance. And let's say that in 1 minute, mice can travel up to a maximum of 8 meters. So if we track our mouse's modeled movement over several minutes, it traces out a sort of janky path. Because of the randomness in direction and distance, our mouse might double back on itself, or even move in circles. This isn't a perfect model, because real mice make all kinds of decisions that can't be easily captured with math, but it does capture some of the spontaneity of a mouse's behavior. The neat thing is, at every point, we can work out how far our radioactive mouse is from its starting location, which is the information that we're after. We can even simplify our Brownian-motion model a little bit more, because what we're really interested in is the mouse's total distance away from its starting point. So, instead of tracking all the possible directions the mouse could travel, we can think about its movement in just 2 directions along a number line. The left side of the number line is negative numbers, and the right side of the number line is positive numbers. Specifically, we can say that the starting point, or the radioactive source, is 0. Then the mouse moves some distance up to a maximum of 8 meters, left or right, every minute. Programming languages work really well with math, so this will make our lives a lot easier when it's time to code. The final distance from the radioactive source will just be the difference between wherever it ends up on the line and its starting point of 0. And now we have the basic outline of our program, which means that we're ready to jump into some Java code. First up, we'll import the scanner and the math class from the Java standard library, as we've done for other radioactive mice programs. Inside the main method of our program, we'll define some key inputs. First, we'll prompt the user to input how long in minutes we want to model the mouse's motion, which we'll save to a double variable called travel time. Then we'll define a double variable called total distance, which represents the total distance of the mouse from the point where it ate the radioactive material. To start, we'll set this variable to 0 meters. Now we need to model the movement of the mouse. Just like we planned in our program outline, we'll use the idea of a Brownian-motion model, but with a number line for simplicity. Every minute, the mouse will move a random distance, left or right, from whatever point on the number line it's currently on. Like if the mouse is at 6 and the random distance is set to -2, it moves 2 steps to the left and winds up at 4. The next minute, the mouse might have a random distance of 5, move 5 steps to the right, and end up at 9. We'll track each movement by adding a random number between -8 and 8 to our total distance for however many minutes that we're modeling the mouse's motion. If you sense a loop coming up, you'd be correct. To code this loop, we first need a way to generate random numbers between -8 and 8, so we'll create a method called random distance, where we define the maximum and minimum values of our distance, 8 and -8, and then return a random number between them. Conveniently, Java gives us a way of generating random numbers. In the math library, we can call the math.random method, which automatically returns a random number between 0 and 1. That's close to what we want, but not exactly it. We need to adjust the range to match our model by doing some mathematical tweaks. Specifically, we can stretch out the 0 to 1 range by multiplying math.random by the difference of the maximum and minimum values. 8 minus -8 is 16. Even though it's a step closer, 0 to 16 still isn't the -8 to 8 range that we want. But we can do one final mathematical tweak and add the minimum value, -8, to the whole interval. And voila, we have successfully modified the value returned by the math.random method, which was 0 to 1, to the range of -8 to 8. We can then assign the value of this random number to a new double variable named distance and return it at the end of our method. So every time we call the random distance method, it will return a random value between -8 and 8, including numbers with decimals, because remember, a double can have decimal places. And now we are ready to bring in a for loop. We want to calculate the total distance away from the starting point, which will be the sum of the distance the mouse moves each minute for whatever number of minutes we entered in the initial prompt. Adding up a whole bunch of numbers a fixed amount of times is precisely what for loops are best at. First up, we need to add the information to the for loop parentheses. We initialize our counter, named I, at 0. We set the condition that I has to be less than the travel time variable, so that we can execute the loop as many times as the number of minutes. And we increment the counter by 1 after every loop. Then, inside the curly brackets, we'll add the value from calling our random distance method to the total distance variable. That way, as our loop runs, it simulates the motion of the mouse each minute by adding the random distance moved to our total distance. It's our simplified Brownian-motion model in action. As a final step, we need to print the absolute value of the total distance variable. This will tell us how far our mouse moved from the starting point after a certain number of minutes. We're specifically using the absolute value because we just want the total distance. We don't care whether it ended up left or right on the number line. We just want to know how far it got. For instance, we could execute our code with an input of 60 minutes. After the for loop does its thing 60 times, our program might give us an answer of 41.8 meters. But because our model relies on Brownian-motion's random distances, we could run our code again with the exact same input and get 34.5 meters. Or if we give an input of 300 minutes, we might get a total distance traveled of 52.9 meters, which is not 5 times the result we were getting for 60 minutes. It can be a little tricky to wrap our brains around this idea of random movement, because the for loops we've seen in other episodes just return bigger and bigger numbers. All the same, this model gives us a general idea of how far a dangerous mouse might spread its radioactivity over time. In fact, with the power of for loops, we can make even more thorough predictions by simulating many different radioactive mice over time. Here's the general idea, though you can dive into the details of the code as we go along. We can take the for loop we just coded and package it into a new method called mouse distance, which returns the total distance variable for a single mouse as an output. Then we can create another for loop to get the distances traveled by any number of mice in any number of minutes, and we can print each distance to the terminal. The cool part is that when we look at all of these numbers together, like if we copied them into a spreadsheet, we can visualize the distribution of distances that our modeled radioactive mice traveled. For instance, if we simulate 1,000 mice for 15 minutes, we see that most mice haven't gone more than 20 meters, and none further than 50. But if we simulate 1,000 mice for 120 minutes, most mice have traveled far beyond that, and some have even traveled more than 100 meters from their starting location. These kinds of large-scale simulations are helpful for better understanding real-world problems, like working out how radioactive material might spread over time. And we're only able to create simulations like these thanks to the power of loops. Both versions of our program combine loops and methods to automate huge amounts of math in barely a few dozen lines of code. This is the magic of programming. We work out the logic of a problem, identify a way to solve it, pick which tools to use, and then write code to let computers do the hard work for us. The ideas behind methods and loops are two of the most widely used tools in programming, and as you pick up more skills along this journey, you'll be able to take on bigger challenges with less stress. If you're enjoying Study Hall Code and Programming for Beginners and you are interested in taking an online course and earning college credit, check out GoStudyHall.com or click on the button to learn more. Thanks for watching, and see you next time.